3,000 miles of open ocean. No compass, no maps, no instruments. For over 1,500 years, this was impossible, until it wasn't. The Polynesians didn't just sail the Pacific Ocean. They conquered it using knowledge encoded in stones, stars, and memory, a technology more sophisticated than most people realize. They called them the Wandering Stars, 5 bright lights that refused to stay in place. While every other star marched in perfect formation night after night, these 5 traced their own mysterious paths. To ancient Polynesian navigators, these weren't just wandering stars. They were celestial guideposts marking directions, seasons, and sailing windows across an ocean that covered 1/3 of the Earth. But the wandering stars were only part of an entire navigation system, one that read the ocean itself like a 3-dimensional map, written in waves, birds, and light. The Pacific Ocean covers 63 million square miles, larger than all of Earth's landmasses combined. Polynesian islands scattered across it are like grains of sand on a football field. Their canoes were masterpieces of engineering. 2 hulls, lashed together with coconut fiber rope. No metal, carrying 80 people and supplies for months. A journey to Hawaii from Tahiti. 2,400 miles across open ocean. 1 degree off course, and you miss the islands entirely. Sailing into emptiness until your supplies run out. So, they memorized the sky. Not just the brightest stars, but hundreds of them, their rising points, setting points, and the exact moment each one crossed overhead. The 5 wandering stars, Venus, Jupiter, Mars, Saturn, and Mercury, became celestial clocks, telling navigators when to sail, when to wait, and which direction would lead them home. Beneath the surface, the ocean was speaking. Swells crossed at different angles, currents pushed in contrary directions, and water temperature told stories about land hundreds of miles away. Navigators could feel wave direction by reading the motion of the canoe, sensing swells that had traveled 1,000 miles, bent by islands still over the horizon. And then there were the birds. Frigatebirds roost on land, but fish far offshore, meaning a frigatebird heading somewhere in late afternoon is heading home, toward land. Before every voyage, the entire community prepared. Not just the navigators, everyone. Because navigation knowledge was too precious to risk on one person. None, 2, M, 2. The star compass wasn't a physical object. It was a mental construct, dividing the horizon into 32 houses, each house owned by a rising or setting star. When sailing toward Hawaii, they'd keep the rising point of Arcturus on their left bow. As long as that star rose in the correct position night after night, they knew their course was true. OD, Venus, the brightest of the wandering stars, rose before the sun, telling navigators the exact moment of dawn and confirming their eastern heading. Jupiter marked the seasons. When it appeared in a certain house of the star compass, navigators knew sailing season had arrived. Calm winds, predictable currents, survival weather. Mars, red and unmistakable, warned of weather changes. Its position told navigators if storms were brewing in their path or if safe passage was likely. Saturn moved slowest of all the wandering stars, taking 29 years to circle the sky, a generational timekeeper, helping navigators track long-term climate cycles. Mercury was the trickster, appearing only briefly after sunset or before dawn, hugging the horizon. Spotting it required perfect conditions and proved a navigator's skill. While fixed stars circled the celestial pole in perfect formation, these 5 traced their own rebellious paths, wandering forward, sometimes backward, writing cosmic equations across the night. Each wave set had traveled from a different storm, hundreds or thousands of miles away. Reading their intersection told navigators about weather systems across half the Pacific. Frigatebirds never land on water; their feathers aren't waterproof. So when you see them flying toward the horizon in late afternoon, they're heading to land, sometimes visible 80 miles away to a bird's eye. Certain clouds don't move. They hover over islands, created by warm air rising from land. A stationary cloud on the horizon meant land beneath it, sometimes 30 miles before you could see the island itself. The underside of clouds changed color when passing over lagoons, picking up turquoise reflection from shallow water. Navigators could see islands in the clouds themselves, 20 miles before landfall. Watercolor told depths. Dark blue meant thousands of feet deep. Lighter blue meant underwater mountains rising, which meant land nearby, even if still below the surface. Temperature mattered. Currents flowing from different directions had different temperatures, warmer from equator, cooler from polar regions. A 1-degree change told navigators they'd crossed into a new current system. Dolphins sometimes guided canoes toward fish-rich waters, which meant nutrient upwellings, which meant underwater ridges, which meant navigators had crossed into a new region of the ocean. Even plankton told stories. At night, they glowed when disturbed, and their glow patterns showed which way currents were actually moving beneath the canoe's direction of travel. Salinity varied. River runoff from islands made water slightly less salty, detectable to trained taste. A navigator could taste an island's presence before seeing or smelling it. Flying fish meant shallow water ahead. They don't fly far from reefs. And where frigatebirds hunted flying fish, land was within a day's sail. First night's navigation was critical. The home star, the rising point they'd left behind, had to align perfectly with the canoe's wake. 1-degree error now meant 100 miles off course later. By day 3, navigators could identify 7 different swell types by touch alone, each from a different distant storm system, each providing directional information. Week 1. No land, no birds, no cloud signs, only the sun's arc, the star paths at night, and the memory of wave patterns learned from masters, who themselves learned from masters going back 60 generations. The most skilled navigators could track Venus, even during daytime, using the brightest wandering star to check course when other stars were invisible. A technique that separated masters from students. Week 2. The first frigatebird in 8 days. Not circling, flying with purpose toward a specific point on the horizon. Land was close, maybe 40 miles. The hardest part of the journey nearly complete. The standing cloud appeared exactly where the star paths predicted. 16 days at sea, 1,500 miles traveled, and the island was precisely where the ancestors' knowledge said it would be. The green flash at sunset, a phenomenon requiring perfect conditions, was considered a message from the ancestors. You navigated well. Land tomorrow. 17 days after leaving sight of land, they arrived at an island, 70 miles long, in an ocean, 63 million square miles wide, guided only by stars, waves, and knowledge encoded in memory. The science behind it was precise geometry. Arcturus rises at 19 degrees north latitude, exactly where Hawaii sits. Keep that star rising on your left bow from Tahiti, and you cannot miss the islands. They weren't fighting the ocean, they were using it. Trade winds blow east to west. Ocean currents flow in predictable gyres. Knowing these patterns meant thousands of miles of assistance instead of resistance. Modern GPS satellites orbit at 12,000 miles altitude. Polynesian navigators achieved equivalent accuracy using points of light 93 million miles away. The wandering stars that marked seasons, directions, and time. In the 1,970 seconds, anthropologists were skeptical that ancient navigation could work. So Polynesian masters built traditional canoes and sailed them Hawaii to Tahiti to New Zealand, using only stars, waves, and birds. One man, Master Navigator Mau Piailug, still held the complete knowledge. He sailed from Micronesia to Hawaii in 1976 with 0 instruments, teaching a new generation of Hawaiians what had nearly been lost. The canoe Hōkūleʻa has since sailed over 200,000 miles, using only traditional navigation, proving the ancient masters accomplished something modern science said was impossible. Genetic analysis confirms it. Polynesians settled islands, from Indonesia to Easter Island, Hawaii to New Zealand, 10,000 miles across the Pacific, between 800 CE and 1,300 CE, using nothing but traditional navigation. The archaeology is definitive. They brought pigs, chickens, taro plants, and breadfruit, proving these weren't accidental drift voyages. Every island was deliberately found, settled, and colonized. Cultural similarities across 5,000 miles of ocean prove ongoing contact. They didn't just settle these islands once they sailed back and forth, maintaining trade and family connections for generations. Easter Island, the most remote inhabited island on Earth, was found and settled by Polynesians around 1200 CE. To reach it required sailing into prevailing winds and currents, then navigating back against them to report success. Rare planetary alignments marked momentous occasions. All 5 wandering stars visible together occurred maybe twice in a navigator's lifetime. Remembered in oral histories and chants passed down through generations. Navigation knowledge was encoded in chants, songs that listed star positions, current patterns, and wave types. The rhythm made memorizing thousands of data points possible, storing an entire navigation database in human memory. Today, navigation schools across Polynesia teach the ancient techniques. What nearly disappeared in the 20th century is being preserved not as history, but as living knowledge passed from master to student exactly as it was 1,000 years ago. Modern science no longer dismisses traditional navigation as myth or luck, it studies it. Meteorologists and oceanographers have learned new ways of reading weather and current by understanding what navigators knew through observation. They mapped the Pacific's major current systems without satellites or instruments, pure observation across generations, noting where warm and cold water met, where gyres circulated, where upwellings occurred. Each island had its signature birds. Frigatebirds nested in specific atolls. Boobies preferred others. Knowing which bird species meant which island helped navigators identify exactly which landmass they'd reached, even before seeing it clearly. Bioluminescence patterns changed over reefs. Plankton glowed brighter in shallow water, dimmer in deep, creating a living depth finder that showed underwater geography at night when visual confirmation was impossible. Star trails revealed the celestial pole, the pivot point, around which the night sky rotated. Keeping that pole at a constant angle to the canoe maintained latitude. The wandering stars confirmed seasonal timing and longitude references. Zenith stars, stars that passed directly overhead, marked precise latitudes. Arcturus at zenith meant you were at 19 degrees north Hawaii's latitude. Different islands had different zenith stars, creating a celestial coordinate system. Waves refract around islands like light through a lens. Navigators could detect this refraction pattern 30 miles from land, feeling wave crossings that told them an island was ahead before any visual confirmation. When Europeans first encountered Polynesian navigators, they couldn't comprehend navigation without instruments. It seemed like magic until the navigators consistently reached destinations. Europeans required maps and sextants to find. Trade winds, consistent wind patterns between 30 degrees N and 30 degrees S latitude, blow west to east year-round. Polynesians understood this system, timing voyages to use trade winds as reliable engines, pushing them thousands of miles. The moon joined the navigation orchestra. Its phase marked days within the month. Its position indicated time of night. Its pull affected tides. Nothing in the sky or ocean was observed in isolation. Even coral reefs had distinct signatures. Hawaiian reefs looked different from Tahitian reefs. An experienced navigator could identify which island group they'd reached by the coral formations visible in shallow lagoons. Frigatebirds could see land from altitudes the canoes never reached. A bird heading purposefully toward a point still over the horizon told navigators land was there, sometimes 80 miles away, visible only from a bird's height. Traditional weather prediction was sophisticated, reading cloud heights, formations, colors, and movement patterns to predict storms hours or days ahead. Navigators routed around weather systems. Modern forecasters track with satellites. Advanced navigators could detect 5 or 6 different swell sets simultaneously, each from a different distant storm system, creating a three-dimensional grid across the ocean, more reliable than any compass. The navigation renaissance began in 1973, when island elders realized the knowledge was dying. Now, navigation schools across Polynesia teach traditional techniques, ensuring the wandering stars will guide canoes for generations to come. The wandering stars still wander their same paths. Venus still rises before the sun. Jupiter still marks the seasons. The same celestial dance that guided canoes 1,000 years ago guides them today. Modern GPS accuracy, 5 to 10 meters. Traditional star navigation accuracy, reaching a 40-mile wide island after sailing 2,000 miles better than 1% error. Different technologies, equivalent results. Birds and navigators, reading the same signs, clouds, stars, waves, both finding land in an infinite ocean, both part of the same ancient knowledge system that conquered the largest ocean on Earth. Every successful voyage proved what modern science doubted for decades, that human observation, memory, and skill could achieve what seemed impossible. Precise navigation across 1/3 of the Earth's surface. The wandering stars still wander. The fixed stars still circle the pole. The waves still carry messages from distant storms. And navigators still read them all, proving that the most sophisticated technology isn't always the newest, but the one that works in harmony with nature itself.